Next, we continue with the same pricing model introduced in the last video, but this time we're going to use a power curve, okay, for modeling the demand. Power curve is used when a nonlinear relationship between the price and the demand is suspected. This is generally the case, and especially if we know or have a good estimate for price elasticity. The form of power curve is D equals A times B to the power of B, where negative B, in our case negative 2, is the known, it comes from the known price elasticity of 2. Okay, so this B parameter, right, is also interpreted as the speed with which the demand decreases as the price increases. The constant A is simply the demand for the product price at $1 per unit, right, and is calculated for the current price and demand levels, as will be demonstrated shortly in the Excel file. When we don't know the elasticity of the curve, but believe that demand has a nonlinear relationship with price, which it pretty much always does, we typically use a polynomial relationship, such as a quadratic curve, shown here almost at the bottom of the slide, right? D is equal to A times B squared plus B times B plus C. One way or the other, once we have the demand model, either with a quadratic, power, or even linear from the previous video, we then maximize the profit, right, while changing the price, having a constant, presumably constant variable cost, times the demand coming from one of these demand models. Okay, we have also in a reasonable price range we have to restrict it to, and then we will hopefully get the price at which the profit is maximized, which will be demonstrated in Excel as well. So let's switch to it and start by entering a formula for the power curve right here next to the known baseline price of $100. So the power curve is A, which is currently blank or 0, times the price, or P, to the power of, in parentheses, negative elasticity of 2. Okay, so negative elasticity of 2. We have to fix the reference to the elasticity cell as well as the reference to the A parameter. Okay, so of course we're going to get 0 now because the demand, the baseline is 0. So now to get to the 500 units in demand, we got to type probably some relatively large number here. Okay, let's start with 50. Nothing changes. 5,000. We got a 1. Okay, 50,000. Okay, we got 5, so we're getting the right direction, right? It's probably 2 or 3 more zeros. So 5, how about 5 million? Okay, for 5 million, we're going to get that 500 units of demand we know holds, right, from the previous video, is the assumption behind the price of 100 units, right? Now, all you have to do is copy up and then down this relationship. Okay, and you'll notice that for $110 in price, for example, the demand is estimated to about 413 units, which is relatively close to the 400 coming out of the linear model from the previous video. However, if we increase the price in the linear, right, for example, all the way to 150, as I've shown in the previous video, the linear model obviously fails, right? The 0 is just not a reasonable number. The 200 level shown here from the power curve demand model is much better, much more reasonable estimate, right, of what the demand would be for that level of pricing. Okay, on the other hand, right, if we change the price in the linear model to 50, we're going to get 1,000 units in demand, whereas clearly the demand should have been higher because of such a low level of price as captured by 2,000 units over here, right? So I'm going to leave that 110 over there, right? So we're going to save as we go along. Obviously, I'm going to switch to the pricing model and zoom into the top left side of it, right? Notice here that the 3 price demand points are given in this data table and also plotted on this scatter plot below, right? So 50, 2,000, the initial 100 and 500 units, and we approximated for $150 in price about 200 units rather than 222 from the power model before, right? So what we want to do now, we want to scroll down to the chart, right click on it, and then add a trend line. Okay, and then for the trend line, instead of straight line, we're going to pick a polynomial of order 2, and we're going to display the equation on the chart, right? The equation is y equals ax squared plus bx plus c, right? Where the a is 0.24, b is negative 66, and c is 4,700. Okay, capturing this sort of again, nonlinear relationship between the demand and the price, where demand drops off, quickly initially as the price, I guess, either decreases from 100 down towards 50, right? Or the demand increases in that case faster than it does as you move to the right from 100 to that higher end range, where actually you can see the demand, somewhat paradoxically, right, would be a little lower for about 140 a dollar price, and will be a little higher for 150, which is clearly counterintuitive, right? But it will have repercussion in the profit curve, as I'll demonstrate shortly. Okay, so next, what we want to do is we want to calculate the demand, okay, by implementing this, quadratic curve, which is again equals a times x, which is the price currently made up to be $70 squared. I could have had $100. Actually, let me put in 100 just to have that baseline established, right? So again, a times p squared, or x squared, plus b times x, which is times p, plus c, okay, which will of course must be 500 unit, and that of course should have been done in the demand cell rather than the profit cell, right? So then what we're going to do is calculate the profit, which is the difference between the price and unit cost times the just calculated demand. Okay, which is going to be about $25,000 using that baseline price of 100. Then this same profit cell is just simply referenced here, and then this becomes a data table. You highlight the entire data table, including all the price points from 50 to 150 increments of a dollar, the profit reference cell, as well as this blank cell and all the blank cells on the right, and then using data what if analysis data table, and a column input cell, a single input cell of H5 with a price is going to drive all these changes in profit. So this is the same as taking each one of these prices, sticking it into the cell H5, the orange cell, and recording how did the profit change, right? So now I have to zoom, I guess, in quite a bit to get you to see the profit curve, and clearly the optimal price with the maximum profit is around between $80 and $90. Okay, notice because of that anomaly in the demand model here, where there's actually a lower demand for 140, around $140 price point than it is around 150. You have this sort of weird, shape in the curve that does not make sense, right? The profit would, within reality, keep declining as the price goes up, unless something weird, some weird explanation was to be made. Okay, to get the exact price, optimum price, exact maximum, we're going to set up a quick and simple solver by going to add-ins, premium price solver. We're going to set as the objective the profit cell to maximize. Okay, the only variable is the price, which we want to change, and for the constraints we're going to add the fact that the price should be less than, or must be, the price must be less than $150, and the price must be greater than $50. So it's just that boundary range, in which case you don't have to constrain And you don't have to use the make unconstrained variables non-negative because the only one is a price, and it is non-negative because it's between 50 and 100. This is clearly a nonlinear problem. It's smooth, so the standard LS, which I'm guessing stands for least squares, GRG, generalized reduced gradient nonlinear solver, applies, and the solver converges to the current solution. The green checkbox is a good message. We're going to keep it at $83.33 with the highest profit of $28,889, or almost $29,000. Save this, switch to the presentation, and pause.